In this video, we will talk about torque and rotational motion. We will begin by defining torque and the role it plays in rotational motion. We will then proceed with the calculation of torque. We will solve a few problems to demonstrate the concepts presented. Torque is a vector, so it has both magnitude and direction. It can be viewed as a quantitative measure of the effect of a force to produce rotational motion. So in order to define torque, we need two main ingredients. The first one is the force, and the second, because it involves rotational motion, we need to define the axis of rotation. Let's look at the following model. So you have a wheel that is being acted upon by a force F in a tangential direction so as to make it spin in a counterclockwise direction. Because the wheel is spinning, we say that this force is supplying certain amount of torque to it in order to make it rotate about this axis of rotation. The axis of rotation in this case is of course coming out of the screen or out of the plane. So we say the force is providing a torque to this wheel in order to rotate it. So what is this torque? A torque is written with the letter tau, and it is defined as a cross product of two vectors. The first is a position vector, which we'll define in a minute, and the second is the force vector, that is this one. So what is this position vector that we are referring to here? The position vector here is defined as the position vector of the point at which the force is acting. So it extends all the way from the axis of rotation to the point where the force acts. Since the position vector is measured in the unit of meter and force is measured in the unit of Newton, torque has an SI unit of Newton meter. What about the direction of this torque? Note that the vector r is going that way, and vector F, the force vector, is going that way. And if you curl your right hand fingers from vector r to vector F, because vector r is the first vector in that cross product and F is the second vector in the cross product, so if you curl your right hand fingers from r to F, your thumb will be pointing out of the plane. So the direction of this torque in this case is out of the plane. We will usually apply the following convention for the sign of the torque. If the rotation is counterclockwise, or the direction of the torque is out of the plane towards you, we will take the sign of that torque to be positive. Likewise, if the direction of rotation now is clockwise because the direction of the force is going opposite to that given earlier, we see that the force is going in that direction, torque, the position vector is going in that direction, so the torque will be going into the board, because as you curl with your right hand fingers from the position vector to the force, you will see the direction of your right hand thumb will be pointing into the plane. So that means for a clockwise of rotation, which means when the torque is heading into the plane, the sign of the torque is taken to be negative. So that is the sign convention for the torque. Regarding the magnitude of the torque, due to this cross product relation, the magnitude of the torque is written as the magnitude of the position vector, that is that distance right there, times the magnitude of the force times the sine of the angle between the two vectors. So in this case, the angle between these two vectors is 90 degrees, sine 90 is 1, and the torque simply becomes R times F. Let's look at the following system. So here you have a rod of length r meters, and this is the axis of rotation, and this rod, it's being acted upon by a force F, and this force is acting at some angle theta. So the direction of the torque is given by this following cross product. So this is the position vector, and if we extend the position vector, the direction is like that. So that is the angle. That is the direction of the position vector. And if you curl your right hand fingers from R to F, you see that the direction of your thumb is pointing out of the plane. So that is the direction of the torque for this rod. And it's moving counterclockwise, so we say the torque is positive. The magnitude of the torque in this case is given by the length of the rod times the magnitude of the force times the sine of that angle, the acute angle right there. So this is the magnitude of the torque in this case. And it has a positive sign, as we have explained before. Let's look at some numerical cases to highlight the effect of angle on the value of the torque. So here you have a rod. This is the axis of rotation. The length of the rod is 4 meters, and the amount of force that is acting at the tip of the rod is 20 newtons in that direction. So we see that that is the direction of the position vector, and that is the direction of the force. And the angle between them happens to be 90 degrees. So we determine the torque for this case. It is quite simply 4 times 20 times sine 90, which is simply 80 Newton meters. And the direction of the torque is, of course, as you can see, because the rotation is counterclockwise, the direction of the torque is coming out of the board, and therefore the sign for the torque is positive. Now the same rod is being acted upon by the same amount of force of the same magnitude, but at slightly different angle. So as you can see, the force is heading that way. The position vector is going from the axis of rotation to the right, so you can sketch it that way. So that is force, that is the position vector, and the angle between them is 120 degrees. So the right hand rule will again give you the torque direction as out of the board, meaning it is rotating the rod in a counterclockwise manner, which means it has a positive sign, and the magnitude of the torque is given by 20 times 4 times sine 120, and that's going to be 69.3 Newton meter. What about this case? Now, as you can see, the force is acting on the axis of rotation. So that is the direction of the force. And since the force is acting on the axis of rotation, the position vector of the point on which the force is acting is 0. So that means there is no torque in this case, which means there is no rotation as one should expect. Remember, the position vector in the equation for torque extends from the axis of rotation to where the force acts. So in this case, the axis of rotation and where the force acts is the same point, so resulting in 0 vector, null vector for the position vector, thus giving 0 Newton meter for the torque, resulting in no rotation. Let's look at this case. Now the force is directed at an angle of 60 degrees with respect to the rod. So the force is heading that way. The position vector is heading that way. The magnitude of the position vector is 2 meters from the axis of rotation to where the force acts. And the angle is 60 degrees. So that is R, that is F. Now the direction of the torque, which is given by the cross product, as you can see, when you curl your right hand fingers from R to F, your thumb is now pointing into the board. And this is in agreement with the direction of rotation, which is clockwise in this case, resulting in a minus sign for the torque. The value of the torque is given by the position vector, which is 2, the magnitude of the position vector. Force is 20 times sine of 60 degrees, which is 34.6 Newton meter with a negative sign. Last case is as shown here. The force is 20 newtons, but it's directed parallel to the direction of that position vector. So the position vector is heading that way, the force is heading that way, giving an angle of 180 degrees. And we know that sine 180 degrees is 0. That means the resulting torque is 0 Newton meter. So such a force will not rotate this rod. That's the conclusion. So you see the angle between the position vector and the force is very important in determining the magnitude of the torque. Let's do a following problem. A square plate 0.2 meters on each side, as shown in the diagram, is pivoted about an axis through the center and perpendicular to the plate at point O, as shown. So the axis of rotation is right there. So that is the axis of rotation that's coming out of the board. 3 forces are acting on this plate, F2, F1, and F3. What is the net torque about this axis? Let's calculate each contribution separately. Let's do the first force first, which is force 1. The direction of F1 is that way, and as you can see, the position vector extends from the axis of rotation to where the force acts, so it's going to go like that. So that means the angle between the two vectors is, this is 90 and this is 45 degrees, because that is this angle right here. It's 45 degrees because this is a square plate. As you curl your right hand fingers from R to F, your thumb will be pointing into the board. So that means torque due to force 1 will try to rotate the plate in a clockwise direction, or with a minus sign. The magnitude is given by 20 times this length right there, which is, according to Pythagoras' theorem, is given by square root of 0.1 squared plus 0.1 squared, times the sine of 135 degrees, the angle between the two vectors, and that results in minus 2 Newton meter. So that is the torque due to the force 1. Now let's calculate the torque due to force 2. So force 2 is going in that direction, so that's your force 2. Your position vector from the axis of rotation to where the force acts is given by that vector. So that means it's going to go like that. So that's your R2. That's your F2. And this is the angle between them. Again, this is 90 degrees and that is 45 degrees because that angle right there is 45 degrees. The value of the torque for the second force is given by the force 2, which is 15 newtons, and that distance right there is square root of 0.1 squared plus 0.1 squared times the sine of the angle between them, which is sine of 135 degrees, which will give you 1.5 Newton meter. Now, regarding the direction of this torque, when you curl your right hand fingers from R2 to F2, the thumb is going out of the plane. That means force 2 will tend to rotate this plate in a counterclockwise rotation. That means the sign for torque 2 has to be positive. Now torque 3. The R3 is going that way, so this is 45, so this has to be 45, so that means the angle between them is 90 degrees. The direction of the third torque, using right hand rule, is coming out of the board. We'll tend to rotate it counterclockwise, or we'll assume a positive value. The magnitude is 8 times that distance times sine 90, that is this distance right there, which will give you plus 1.13 Newton meter. Adding all three gives you net torque of 0.63 Newton meter.